Let us take an example of a position control system. That is in this figure you will see, in this picture you will see the satellite. Now the search for extra terrestrial life is being carried out with the radio antennas like one pictured here. So it is an example of a position control system. Now the position control system converts the position input command to the position output command, and it is generally used in antennas, robot arms and the computer disk drives. So in this case what we control the antenna azimuth angle. So let's continue the discussion in the next. Now here we have the ISRO antenna which is used to track the Chandrayaan. That is the part of the Indian Deep Space Network. This antenna is actually used to track Chandrayaan, and how it is actually being done, so that we have to see. So our objective in this case is that the azimuth angle change precisely according to the motion of the Chandrayaan. So we have to do this, that how it can be done. So how we can change the azimuth angle? We can use a device which is known as a potentiometer, which converts the angle command into the voltage. So we will use the potentiometer for that very purpose. And in this case, the main purpose of the system to have the azimuth angle output of the antenna follows the input angle of the potentiometer, and this potentiometer converts the angular displacement into voltage. Now the potentiometer will give the signal to the motor. However, the problem is that the motor requires a lot of power, because for moving that antenna, the power required by the motor is large. For that very purpose, we will use the power amplifier. So this system, you will see, it is an open loop system, because there is no means to check whether the change in the angle of the input follows the output, that is, output follows the input. So there is no means. So for that we connect a potentiometer at the output also in this case. Now this output potentiometer actually measures what is the angle, azimuth angle at which the antenna moves. It will give the feedback signal to this differential amplifier, and this feedback signal will generate the difference of the input and this feedback signal, that is actuating signal, and actuates the motor if the output is not following the input. So we use another potentiometer to check whether actually the output is following the input, and then that difference is actually used to derive the system in this case. So this is how we have made a open loop system into a closed loop system by connecting the feedback terminal, that is the potentiometer, and then create the difference of input and the output. Now this is the schematic, that how it works, that it sees that input is the potentiometer. We are changing the potentiometer, that is converted into the voltage, then it goes to differential and the power in amplifier, and then to the motor. Motor will rotate, and then it will change the position of that antenna. Now also in the output you will see that the position of the gear, or the change in the angular position of the gear, is taken by that potentiometer at the feedback, and that is given to the differential and the power amplifier. So this is the whole of the structure, that is schematic. Now after the schematic we will have the functional block diagram, that is this block diagram, that is the D, figure number D. Now in this block diagram you will see that we will have the angular input, and potentiometer acts as an input transducer which is converted into the voltage which is proportional to the input, and then summing junction which generates the actuating signal, and after that we have the controllers which are power amplifiers, and after that the motor load and the gears, that is plant, are the process, and then finally we are getting the angular output. And at the output we will get the angular displacement through that potentiometer. It is converted into voltage and given to the summing junction. So this is how the functional diagram has been made. So this is actually the functional diagram on which we have to work on. Also in the schematic you see that since we have considered that the dynamics of the amplifier is rapid and the response term is very less, so we have taken the gain of the amplifier as K only. Now here we will study about the effect of the gain on the response of the controller. Here we will see that two curves are there. One is for the high value of the gain and the other is for the lower value of the gain. And now you will see that if the gain is increased, then for a given actuating signal the motor will be driven harder, and as a result we can reach the input in a very small amount of time. However, because of the inertia, some motor it turns faster to the final position. Because of inertia the overshoot is there, and finally after some oscillations it will reach to the final steady state position, that is damped oscillations are there in this case. And in case of steady state, so the steady state reaches when the transient is 0, and typically if the gain is more, then the steady state error is less, and if the gain is less, then the steady state error is more. So the steady state error decreases with the increase in gain and increases with the decrease in gain. However, in some cases the steady state error will not be 0, and for these systems a simple gain adjustment to regulate the transient response is either not effective or leads to the trade-off between the desired transient response and desired steady state accuracy. Now solve this type of problem that we discussed in the last slide. A controller with the dynamic response, that controller, that is the electrical, that is called the electrical filter or the compensator, along with the amplifier can be used for. With this type of controller, it is possible to design both the required transient response and required steady state accuracy without the trade-off required by simple setting gain. So this controller with the dynamic response is known as the compensator.